Topic of my presentation is steam turbine. It is mostly used in power generation systems. So let us start with main contents, which are introduction, that is, what is a steam turbine and how does it work? Types of steam turbines. Applications of steam turbines. Advantages and disadvantages of steam turbines. A steam turbine is a device that extracts thermal energy from the steam and converts it to mechanical work on a rotating output shaft. A steam turbine is a device that converts the thermal energy of pressurized steam into mechanical or electrical energy. It works by using a series of blades attached to a rotating shaft that are pushed by the high-speed jets of steam. The steam turbine was invented by Charles Parsons in 1884 and is widely used in power plants and other applications. Main parts of a steam turbine are casing, rotor or wheel, blades or vanes, bearings, seals, governor system, support system. Casing of steam turbine is connected to the higher pressure steam supply line and the low pressure steam exhaust line respectively. The steam chest connected to the casing houses the governor valve and the overspeed trip valve. The casing contains the rotor and nozzles through which the steam is expanded and directed against the rotating buckets. A rotor or wheel of a steam turbine is the part that rotates and transfers the mechanical energy from the steam to the generator or the driven machine. It consists of a shaft and disc assemblies with blades or buckets attached to them. The blades or buckets are shaped to capture the kinetic and pressure energy of the steam and convert it into rotational motion. The rotor is supported by bearings and enclosed in a cylindrical casing. Blades or vanes of a steam turbine are the parts that are attached to the rotor or wheel and interact with the steam flow to produce rotational motion. They are shaped like aerofoils and have different angles and profiles depending on the stage of the turbine and the design of the engine, and are classified into moving blades and fixed blades. The blades or vanes are responsible for extracting energy from the high temperature, high pressure steam and converting it into mechanical work. They are subjected to very strenuous environments inside a gas turbine, such as high centrifugal forces, thermal stresses, erosion, corrosion, fatigue, and vibration. To withstand these conditions, they are made of special materials such as superalloys, ceramics, or composites, and they are often cooled by air or steam. Bearings of a steam turbine are the parts that support the rotor and allow it to rotate smoothly and safely. There are two main types of bearings in a steam turbine: thrust bearings and journal bearings. Thrust bearings are used to bear the axial force of the steam and the coupling acting on the rotor. Journal bearings are used to support the weight of the rotor and reduce friction between the rotating shaft and the stationary casing. Seals of a steam turbine are the parts that prevent or reduce the leakage of steam between different pressure regions in the turbine. They are essential for improving the efficiency and reliability of the turbine. There are different types of seals used in a steam turbine, such as carbon ring seals, labyrinth seals, mechanical seals. A governor system of a steam turbine is a part of the turbine control system that regulates the rotational speed of the turbine in response to changing load conditions. The governor system consists of a speed sensor, a controller, and an actuator. The governor system ensures that the turbine operates at a constant speed or frequency regardless of the variations in load or steam pressure. It also protects the turbine from overspeeding or underspeeding. The governor system also helps to maintain the stability and efficiency of the power system by balancing the supply and demand of electricity. There are different types of governor systems used for steam turbines, such as throttle governing, nozzle governing, bypass governing, and electrohydraulic governing. A support system of a steam turbine is a part of the turbine that provides auxiliary functions such as lubrication, cooling, sealing, governing, and protection. The support system is essential for the safe and reliable operation of the turbine and the power plant. A steam turbine works by using a heat source, such as gas, coal, nuclear, or solar, to heat water to extremely high temperatures until it turns into steam. The steam then flows past the spinning blades of a turbine, which are shaped to capture the kinetic and pressure energy of the steam and convert it into rotational motion. The turbine is connected to a generator or a driven machine, which uses the rotational motion to produce electricity or perform mechanical work. Some of the common types of steam turbines are impulse turbine, reaction turbine, back pressure turbine, extraction turbine, condensing turbine, radial flow turbine, axial flow turbine. Depending on pressure, types of steam turbine are low pressure, intermediate pressure, and high pressure. An impulse turbine is a type of turbine that uses the kinetic energy of a high-velocity jet of water or steam to rotate the turbine blades and generate electricity. The impulse turbine works on the principle of Newton's second law, which states that the force acting on an object is equal to the change in its momentum. The impulse turbine gets its name from the impulse force generated by the water or steam jet hitting the blade. There are different types of impulse turbines, such as Pelton wheel turbine, turbo turbine, and cross-flow turbine. Impulse turbines are simple and inexpensive, but they have lower efficiency and higher losses than reaction turbines. A reaction turbine is a type of turbine that develops torque by reacting to the pressure or mass of a gas or fluid. The operation of reaction turbines is described by Newton's third law of motion, which states that the action and reaction are equal and opposite. In a reaction turbine, the fluid enters the rotor under pressure and flows over the blades, causing them to rotate. The fluid changes its pressure and direction as it passes through both the fixed and moving blades, and it reacts with the blades to produce a force. There are different types of reaction turbines, such as propeller turbines, Francis turbines, gravity turbines, bulb turbines, Straflo turbines, tube turbines, and Kaplan turbine. A back pressure turbine is a type of steam turbine that does not condense the exhaust steam, but instead uses it for other purposes, such as heating or process steam. Back pressure turbines are used to generate power while also providing useful steam for industrial or commercial use. They have higher efficiency and lower capital cost than condensing turbines, but they produce less power per unit of steam. Back pressure turbines are commonly found at refineries, district heating units, pulp and paper plants, and desalination facilities where large amounts of low-pressure process steam are needed. The electric power generated by the back pressure turbine is directly proportional to the amount of process steam required. An extraction steam turbine is a type of steam turbine that can extract some of the steam from different stages of the turbine and use it for various purposes, such as heating, cooling, or other industrial processes. An extraction steam turbine can have single or multiple openings in its casing for the. Some examples of extraction steam turbines are extraction condensing turbines, back pressure turbine, reheat turbine. Condensing steam turbines are mostly used for power generation, as they can produce more power per unit of steam than back pressure turbines or extraction turbines. Condensing steam turbines have very low exhaust pressures, typically below atmospheric pressure, which increases the power output. Condensing steam turbines have lower thermal efficiency than cogeneration turbines, as they reject a large amount of heat to the cooling utility. However, they can still achieve higher efficiency than conventional power plants by using superheated steam and reheat cycles. Condensing steam turbines can be combined with other heat engines, such as gas turbines or internal combustion engines, to form combined cycle power plants that can achieve higher overall efficiency and lower emissions. Some points about radial flow steam turbines are: radial flow steam turbines can have different flow directions, such as inward flow, from a larger to a smaller diameter, or outward flow, from a smaller to a larger diameter. The flow direction affects the performance and design of the turbine. Radial flow steam turbines can achieve higher pressure ratios and lower flow rates per stage than axial flow steam turbines. This makes them suitable for lower specific speed and power ranges. Radial flow steam turbines can be simpler, more robust, and more efficient than axial flow steam turbines in a similar power range, as they have less mechanical and thermal stresses. However, for high power ranges, above 5 megawatts, radial flow steam turbines are no longer competitive due to their heavy and expensive rotors. Radial flow steam turbines can be used for various applications, such as power generation, cogeneration, or industrial processes. Some examples of radial flow steam turbines are France's turbines, inward flow, Lundstrom turbines, outward flow, and Hero's turbines, outward flow. Some points about axial flow turbines are: axial flow turbines are turbines in which the working fluid flows parallel to the shaft, as opposed to radial turbines, where the fluid runs around a shaft, as in a water mill. Axial flow turbines have a similar construction as an axial compressor, but they operate in reverse, converting flow of the fluid into rotating mechanical energy. Axial flow turbines can have different flow directions, such as inward flow or outward flow. The flow direction affects the performance and design of the turbine. Axial flow turbines can achieve higher pressure ratios and lower flow rates per stage than radial flow turbines. This makes them suitable for lower specific speed and power ranges. Axial flow turbines can be simpler, more robust, and more efficient than radial flow turbines in a similar power range, as they have less mechanical and thermal stresses. However, for high power ranges, above 5 megawatts, axial flow turbines are no longer competitive due to their heavy and expensive rotors. Axial flow turbines can be used for various applications, such as power generation, cogeneration, or industrial processes. Some examples of axial flow turbines are France's turbines, inward flow, Lundstrom turbines, outward flow, and Hero's turbines, outward flow. Low-pressure steam turbines are turbines that produce low-pressure, LP, exhaust steam that can be used for various purposes, such as heating, cooling, or other industrial processes. Low-pressure steam turbines can improve the efficiency and flexibility of the turbine and reduce the fuel consumption by extracting some of the steam from different stages of the turbine. Low-pressure steam turbines can have different configurations, depending on the application and the desired output. Low-pressure steam turbines can produce approximately 60 to 70% of the gross power output of the power plant unit. Low-pressure steam turbines receive superheated steam from a moisture separatory heater, MSR, or from the main steam lines. The steam expands and loses pressure and temperature as it passes through the turbine blades. The exhausted steam then condenses in a surface condenser or is used as a heat source for process applications. Steam turbines are: intermediate pressure steam turbines are turbines that have one or more controlled steam extractions at intermediate pressures for various purposes, such as heating, cooling, or other industrial processes. Intermediate pressure steam turbines can improve the efficiency and flexibility of the turbine and reduce the fuel consumption by extracting some of the steam from different stages of the turbine. Intermediate pressure steam turbines can have different configurations, depending on the application and the desired output. Intermediate pressure steam turbines can produce approximately 20 to 30% of the gross power output of the power plant unit. Intermediate pressure steam turbines receive superheated steam from a high-pressure turbine or from the main steam lines. The steam expands and loses pressure and temperature as it passes through the turbine blades. The extracted steam is then used by consumers at a constant pressure, regardless of the turbine load. The remaining portion of the steam passes to the subsequent turbine stages or to the condenser. A high-pressure steam turbine is a machine that uses pressurized steam to do mechanical work on a rotating output shaft. It is a type of heat engine that improves its efficiency by using multiple stages of expansion of the steam. A high-pressure steam turbine usually consists of an impulse control stage followed by reaction blading in each end of the element. It produces about 30 to 40% of the gross power output of the power plant unit. It receives steam from a steam generator and exhausts it to a moisture separatory heater. The steam is then reheated and directed to the low-pressure stage of the steam turbine. High-pressure steam turbines are widely used in thermal power stations, nuclear power plants, geothermal plants, and solar power plants. They are also used in marine propulsion and naval warfare. Here are some applications of steam turbine. Steam turbines are a part of various industries, from medium to large scale, and include dozens of institutional applications. Chemical industry, providing heat and electricity to drive different processes in the chemical and pharmaceutical industries. Steam turbines are integrated in the process of producing power. Waste plants, steam turbines help generate the power needed to harness energy from wastes. Oil and gas, used as a pump drive or a compressor, steam turbines support dozens of operations in the oil and gas industry. Sugar mills, offering high levels of efficiency and sustainable operations, steam turbines are used to produce green carbon dioxide energy from bagasse. Combined heat and power. Driving mechanical equipment. District heating and cooling systems. The efficiency of steam turbines is the ratio of the output work or energy to the input heat or energy. There are different types of efficiency that can be used to measure the performance of steam turbines, such as thermal efficiency, overall efficiency, blade efficiency, nozzle efficiency, stage efficiency, and isentropic efficiency. The efficiency of steam turbines varies depending on the design, size, and operating conditions of the turbine, but it is typically between 30% to 90%. While steam turbines offer a quick and efficient way to produce power, they require a thermal energy source to operate. The following are different sources of energy that can drive a steam turbine. Coal. Fossil fuels, natural gas. Geothermal. Nuclear. Some of the best practices for steam turbine maintenance and operation are: use reliable valves with high shutoff class to regulate the steam flow. Use appropriate hanger supports, guides, expansion joints, and bellows to prevent excessive forces or moments on the turbine flanges. Use proper filtration and cooling systems to prevent oil contamination and degradation. Use appropriate welding, machining, coating, and balancing techniques to restore the component integrity and functionality. Follow the proper procedures and safety precautions during the disassembly, reassembly, alignment, and testing of the turbine. Few among the advantages of steam turbine are: high thermal efficiency compared to reciprocating engines. High power-to-weight ratio compared to reciprocating engines. Fewer moving parts than reciprocating engines. High reliability, especially in cases where sustained high power output is needed. Less vibrations compared to reciprocating engines. Can be designed for greater capacities. Use less lubricant than reciprocating engines. Do not increase the consumption of steam. And in the last, some disadvantages are shown as relatively high overnight cost. Steam turbines are less efficient than reciprocating engines at part load operation. They have longer startup than gas turbines and surely than reciprocating engines. And less responsive to changes in power demand compared with gas turbines and with reciprocating engines. Thanks for watching. That's all for today's video on steam turbines. I hope you found it useful and interesting. I welcome your suggestions in comment box on what topic you want me to cover. If you want to see more videos like this, please subscribe my channel and click the bell icon to get notified whenever I upload a new video. Never forget to like and share.